Hey everyone, thanks for tuning into this session, throwing an AquaWrench into the kernel. Today I want to talk a little bit about this tool, AquaWrench, that I wrote for my team, and talk about what is AquaWrench, what can it do, how does it work, and how can you protect your environment from AquaWrench or tools like AquaWrench. So a little bit about me. My name is Ruben, also known as Beef sometimes. I'm all about hacking Windows on endpoint. That's what I love to do. That's where I spend most of my time. I'm a senior managing consultant on IBM's X-Force Red, and my team specifically is the adversary simulation team. So AquaWrench, what is an AquaWrench? Even me, I'm not totally sure. But essentially, AquaWrench is a bridge that I've built between admin users and the kernel, right? AquaWrench allows the operator to perform data attacks on kernel memory, kernel structures, and all of that. And by doing that, AquaWrench can manipulate OS security and bootstrap unsigned code into the kernel. So if we try to set the scene a little bit, right? As I mentioned already, we require that the local attacker is an administrator or has administrator privileges, right? That's a requirement. The second thing we need to kind of take into account is that this boundary between administrator and kernel is not actually a security boundary, right? If you ask Microsoft, they'll tell you it's not a security boundary. The reason for that is that as an administrator, you have all the permissions that you need in order to load a driver into the kernel. We'll see, like on the next slide, why that can still be problematic, but it is not a security boundary. Finally, when we discuss AquaWrench or tools like AquaWrench and look for real-world examples, what we find is that they are not very common. One example that I give here is White Lambert, which is part of the Lambert's family of malware, right? You have like Black Lambert, White Lambert, Pink Lambert, whatever, all the colors essentially. This is attributed to a three-letter agency. You can use your imagination. And the feature of White Lambert is that it is a driver which sits on top of the network stack. So it's a passive backdoor, essentially. It looks at all the packets that come in on the host, and it looks for some special key identifiers. And if it finds those, it will like perform actions based on those identifiers, right? Whatever those actions may be, like executing code on the host, for instance. So the question is, why is this type of tradecraft uncommon? And I think the answer is really quite straightforward, which is that driver signing requirements are a kind of soft security boundary, right? So I think signature enforcement has been the default since 64-bit Windows Vista, so that's quite a long time. And this requirement kind of prevents arbitrary users from writing some code and just loading it into the kernel, right? So it acts as a kind of gatekeeper to the kernel. So the question is, what can people do then to get their code into the kernel? And I think there are three general options that people can follow. The first is to buy a code signing certificate. Perfectly fine, I suppose. The issue here is that you kind of expose yourself when you do that, right? Because that certificate which is used to sign your driver will have your identifying information on it. So it will tie back to your person, or more likely the entity who purchased the certificate, like your company. The second option is to abuse a stolen or leaked certificate, you'll probably be surprised how many of those certificates are kind of floating around on the internet. And there is a very vibrant game hacking community, and if you look at some of their forums and their threads, you'll easily be able to find those type of things and use them to sign your drivers. The final vulnerability, the final option rather, is to exploit a kernel vulnerability that already exists on the host, or a vulnerability in a third-party driver, right? I kind of bunched those together because they're both vulnerability based. Here I give another example. So there's Turla APT, which is some Russian APT group. In 2014, they had this rootkit, Ouroboros, and they used this ladder technique, right? So with their rootkit, they shipped a driver, vbox-drv.sys, which is a VirtualBox driver, which had a known vulnerability. And then they used that vulnerability to kind of modify the signing requirements in the kernel in memory. And once they achieved that, they were able to load their own second stage payload, right? What I want you to pay attention to as well is that yes, Ouroboros rootkit is old, from 2014, but observe that they actually shipped a driver with a CVE from 2008. So these vulnerabilities are long-lived. People are not really blacklisting drivers, even if they have some known vulnerability. So these types of attacks can be quite dangerous. Right. So I want to dig in a little bit into this vulnerable third-party driver business, or as I like to call it, YOLO driver development. Yeah, it's the Wild West out there, no joke, right? So you can see this tweet here from Firefox, who is an ex-malware researcher, and yeah, he is highlighting in this instance a tool from MSI Smart Tool, which is shipping some vulnerable driver, NTIO lib, whatever it is, right? And he highlights some of the problematic features that this driver has: read-write to MSRs, right? Model-specific registers, physical memory, I/O ports, etc., right? And well, as you can imagine, if you write a driver, you want to talk to it, right? That makes sense. So MSI have included DLL, which is a library kind of for the driver comms. So you don't even really need to reverse the driver. As long as you look through the DLL, it will tell you like how to talk to it, right? That makes sense. Now, this is not an isolated case. The unfortunate truth is that there are many vendors, very reputable vendors, who are writing just like terrible drivers all the time. And I almost guarantee that if you look at some third-party drivers that nobody's ever audited, you will find bugs, basically. Now, Firefox has released this repo, KDU. You can see the link at the bottom of the slide, where he has weaponized nine of these drivers into a framework to kind of demonstrate like some real-world impact of these signed yet vulnerable drivers. I highly recommend that you have a look at that if this is the type of thing that interests you. So yeah, so like I said, yeah, bad coding practices everywhere. So if we kind of remember what the options were, right? The option I went with in AquaWrench is to exploit a vulnerable third-party driver, okay? So after I made this decision, I had to kind of figure out what bug class was best to exploit, because it turns out there are many, right? So some are more useful than others. For instance, there's like a notorious Capcom driver, which you can send it like a buffer of shellcode, and it will just allocate it in the kernel and execute it. Pretty gruesome, as you can imagine. But there are other bug classes like MSR ReadWrite, which technically can be used to achieve arbitrary code execution, but they are difficult to manage essentially. Like the technical details are not like totally important for the purpose of this talk, but with MSR ReadWrite, you can kind of intercept syscalls as they happen and redirect execution, but it requires a lot of things to make it work. Like you need to do kernel stack spraying and manage how threads are being used. It's just like bothersome, right? So the key point is, if we want to use these third-party drivers, we need to find a bug class which is common and which gives us a powerful exploitation primitive that we can use. And so personally, I settled on physical memory mapping in drivers, right? This is also an extremely common capability that developers for some reason like to include in their third-party drivers. Now, you can see here that I say mapping physical memory implies an arbitrary kernel read-write. And maybe that needs to be explained a little bit. So when we think about physical memory, we're talking about memory that lives on chips, right? Like on RAM, or it lives on your hard disk. And when we think about virtual memory, that's kind of an abstraction that the OS kind of fabricates, if you will, right? So you do something on the OS in virtual memory, and then that gets kind of translated somehow through some magic into this belongs here in physical memory, right? So the challenge becomes kind of, can you find out where this thing you want in virtual memory, where that exists in physical memory? And if you can do that, then you can have read-write permissions on those objects that you're interested in. So yeah, so to the point, how does read-write work in AquaWrench, right? And this is a kind of a two-part story, if you will. So the first thing is we have this thing X in ring 0, right, in the kernel. But how do we find the virtual address of X? Is that even a problem, right? Can KSLR save you, right? Because the Windows kernel has ASLR. Now, the truth is that KSLR is not a security boundary for local non-sandboxed users, right? Or non-low integrity users. There are just an absurd amount of functions which allow you to leak kernel pointers and then use them to calculate addresses of other things in the kernel or structures or what have you. So if you're interested in that, I highly recommend that you check out this presentation by Alex Ionescu from RedCon 2013. I got 99 problems, but a kernel pointer ain't one, right? Okay. Now here on the left in this diagram, we can see one of these type of info leaks. This one is very common and very useful at the same time. So it's probably a good example to give. And this technique is used a lot in AquaWrench. So let's say there is a module, right? Test.sys, okay? And we want to find out where a symbol in that module is loaded right now in the kernel, okay? So this is the kind of process that we can do here. We can load this module like with LDR load DLL or load library if you want. And then you can see this yellow block here, LDR load DLL. Once that succeeds, it will give us back the base address of where that module is loaded within our process, right? So you can kind of see that address here in this yellow block here, right? 7FFD9200000, whatever. So that gives us the base address, right? And then once the module is loaded, we can look inside it for the symbol that we're interested in. So whether that symbol is exported, right? So we can maybe do get proc address and get the address of the symbol, or whether we have to employ some other technique like byte pattern-based memory scanning, or whatever the technique may be, right? So we find the symbol that we're interested in here, right, in this blue block, and then we just do a simple calculation, essentially, right? The address of the symbol will be larger than the address of the base address. So if we subtract the symbol here in blue from the yellow block, which is the base address, that gives us some like arbitrary small number. And this number is in fact the offset from the start of the module to the address that we're interested in. Okay, so we just record that value essentially. And then the second part of this is that we use one of these functions which leaks kernel pointers, right? So if we call anti-query system information with the appropriate information class, in this case system module information, it will give us back an array of all the loaded modules in the kernel currently, and what their path is, their name, their size, and their current base address. So that base address essentially bypasses KSLR for us, right? So what we do then is we get from this nice little purple block the base address of the module we're interested in, right? Like test.sys, and then we add the offset to it that we calculated in the starting part, and when we add those together we get this nice red block here, which is the current kernel address of that symbol. So it's a pretty straightforward calculation to do this, right? Now, this is just one example, but there are many types of pointer and structure leaks that exist, okay? Okay, so we can find the address of X in the kernel, right? The virtual address. But remember that our driver is giving us access to physical memory, not virtual memory. So the second part of achieving arbitrary read-write is converting that virtual address into a physical address. Now, there's like a bunch of math involved here, pointer math, and it's not like super important for the purpose of our talk, but if you want to see like some code example and get into the details of how does that work, I wrote some code, vir2phys, which implements this kind of calculating. So you can have a look at the intricate details if you want. But essentially what we do here is that we were able to calculate this address in the red block, right, from the previous step. So that gives us some location in the virtual memory space. And then to find the physical address, we have the driver allocate a bunch of memory at the lower end of the physical memory space, maybe like 10,000 hex bytes. And then AquaWrench will parse that memory until it finds some structures that describe the translation from virtual to physical memory. And once it finds those structures, it can kind of plug in the address we got in red, and through some pointer math, we can get back this yellowy orange address, which is the physical address of that value. So what's important to just drive home here is that this red address and this yellow-orange address, they point at the same memory. So if we modify a value at this red address, we will see that change at the yellow address, and if we modify it at the yellow address, we will see it at the red address, right? So Once we are able to convert our virtual address to a physical address, we've essentially achieved arbitrary read-write. Because at that point, if we want to change this address, we can just tell the driver, hey, allocate me or map me this memory, which is like at 7E254F440. It will do that. You can edit it, and that change will be reflected in the virtual address space. Okay, so kernel read-write, right? What now? Yeah, I just want to say we have to be careful in ring 0. If we put like 1 byte out of place, things can really go pear-shaped. And especially if we want to deploy our tradecraft on business critical machines, we really need to like check our work and make sure we know what we're doing right. But the takeaway here is that at this point, we essentially own the OS. We can patch data structures, modify security constants, repurpose execution vectors or existing memory to run our own arbitrary code, and we'll see examples of that. So that brings us kind of to our first demo that we'll do surrounding protected processes. So protected processes existed already in one form or another since Windows Vista, but in Windows 8.1 they got like a kind of a rework, right? A new and extended model in Windows 8.1. And the key point there was that Microsoft wanted to enable third-party code to kind of opt into being protected, right? And the theory there, I think, like correctly, was that security solutions like AV and EDR were a kind of central point of failure, right? If an attacker achieved administrative privileges, they could just like open a handle to the AV process and kind of render it inoperable, right? So Microsoft wanted to allow those vendors a way to protect their processes against malicious access, right? So in a general sense, protected processes use code integrity to only allow trusted code to load into that process. But at a basic level, what you should consider is that you would not be able to access a process which has a higher protection level than your own process, essentially. Now, again, Microsoft does not consider protected processes a security boundary, and I think you can maybe guess why. The crux of it is that those protected processes are defined in kernel structures, and if you can modify those kernel structures, you can disable that protection. And as we know already, if you're an administrator, getting into the kernel is not a security boundary. So by implication, protected processes are not a security boundary. And as we kind of explained already, these are commonly used to safeguard critical OS components and EDR solutions. Okay, so for the first demo, what we'll do, maybe we should explain this first. So in this case, we have a process X EDR solution, and X EDR solution has an E process structure in the kernel. So all processes in Windows are kind of governed by an E process structure in the kernel, which is like a huge data blob that describes all kinds of features of that process. Okay, and those E process structures are stored in a circular list. So each process on Windows will be in that list, and one will get added if a new process is created and removed if that process gets terminated, right? Now, somewhere within this eProcess structure is a protection object, and as you can imagine, that as the name implies, rather, that protection object actually specifies the protected status of that process. So if you look here at this first yellow block here, protection, you'll see it has an arrow to PS protection, which is a structure, right? So protection is just a pointer which points at this PS protection structure. Now, this structure contains like 3 elements actually. I'm only showing 2 here, but these are the ones that we mostly care about. So this top one, protected light, is like the type of protection, if you want to consider it like that, right? And the second one, anti-malware, is the signer, but the way you can consider it is like, what is the function of this protected process, right? In this case, it's an EDR solution, so its signer will be anti-malware. So what AquaWrench can do essentially is it can look up the eProcess structure for the X EDR solution, and from there it can calculate where the protection object is. It can follow that pointer, and then it's able to read that PS protection structure and change those values, right? So you can kind of see that process here. AquaWrench goes in and changes protected light and anti-malware to none and none, right? So once that's done, then this protection disappears in userland, and an attacker can just open a handle to that process and do whatever they want, just as before. What I want to mention here as well is that this is not the only way for the attacker to gain access to that process. Another option would be that the attacker changes their own protection constants to be of the same level. So for instance, protected light and anti-malware, or of a higher level, right? There's a kind of hierarchy of levels in protection. And once the attacker does that, in the same way, they would be able to access that process based on their own protection status. Okay, so let's have a look at demo 1. Okay, so here for this demo, we're in a Windows 10 64-bit machine, version 1903, as you can see here. And now, since we've never ran AquaWrench here, we first need to load our vulnerable driver that we're going to use. So we can just give it the -L flag. And you can see it loads our driver here. I just want to mention briefly that in this demo, I'm blanking out like the driver name, right? The original checksum and original MD5. I'm not doing that because I don't want to show you what it is. But since we're not releasing this tool publicly, and I have to maintain it, I'd rather not get the driver burned if I don't have to, right? Okay. So our driver loads here, and we can see driver load was a success, right? So now we should be able to use it to do whatever we want. So in a first instance, what we'll look at is here at all of the protected processes. So you can see kind of what we saw on the slide, right? In this case, the protection status of this process here at PID 2288 is the type is light, right? Protected light, and the signer is anti-malware, just like the example on our slide. And if we look at this process, this is Microsoft Defender's anti-malware service, right? Which makes sense. And you can see other types here, right? Light Windows, light WinTCB, full Win system. So you can kind of see the different types of levels that we talked about briefly. So what we're going to do here is we're going to take this PID and we're going to change its protected status so that it is none, just like any other normal process. So To do that, we can just have a quick look at the options for AquaWrench. So these are the ones we're talking about, right? Protect takes a PID, 2288 in our case, and then a protected type, PT, and a protected signer, PS. So for us, it's quite simple, 2288. Let me just double check that, 2288, okay. A PT, a protected type, is none, and a protected signer of none as well. And then you can kind of see that AquaWrench finds out where the eProcess virtual address is, right here in this case, and it does a check for the OS build. So all the functionality in AquaWrench pretty much is gated behind a detailed version check, right? That's to make sure that we never run into a scenario where AquaWrench tries to do something in the kernel where that scenario has not been tested on that actual version. And you can see that in this case, it finds that PS protection structure, like on the slide, protect light, anti-malware, and it goes in and it changes it to none and none, right? Now, if we look here, it hasn't changed. That's just because Process Hacker is not updating that value. So if we just restart Process Hacker here, we can see that this process is no longer in that list, right? So if we sort 2288, you can see that status is now gone, right? And that means that we can actually terminate this if we want now, right? Something we couldn't do before. So that's one option. Something else we can do, as I mentioned, is like, let's say we take Notepad and let's note down the PID. So the PID is 7652. What we can do is set a different protection status for Notepad if we wanted to. Okay, so let's have another look at the options. So P is this, and the protected type, right? You can see this hierarchy we were talking about. So let's go here for protected. Okay, and the PS, or the protected signer. Here you can see where anti-malware fits in on this scale of ascending order of protection. So we can do like WinTCB if we want, why not? Okay, and then we run that, and you can see it goes from none to protected WinTCB. Now if we relaunch this, we can see, look, our Notepad process is here, enjoying one of the highest protections that exist, a highest combination of protections that exist on Windows. Okay, so let's close this. I just want to give one final example. So again, we'll launch Notepad here and note down its PID. So 4480 in this case. Okay, and then we'll have a look at one of the other protected processes, CSRSS, for instance. So if we look at that, we can see that this process protected light is protected, right? Protected light, and the signer is WinTCB. Now, there should be no way for us to open a handle to this process or duplicate a handle from this process, but with AquaWrench, we can do all of that. So if we again have a quick look at the options, we can see there is this duplicate option, right? Source PID to duplicate from, target PID to duplicate to, and a handle to duplicate from the source to the target, right? If we don't specify that handle, then it will open a process handle to that process. So I think we can just kind of open a process handle. Why not? So here we specify ds, duplicate source. In this case is this. No, that's the target, right? Duplicate target, and the source is CSRSS, which is PID 500. Okay. Okay, so we do some tricks here, like the details are not totally important, but essentially we have using some NT functions like NT duplicate object, we've essentially put a handle into Notepad for whatever resource that we wanted access to. Okay, so if we now have a look at Notepad and we look at the handles, we're already at the handles. We can see here there is a process handle to CSRSS, which has a full control as granted access, right? Something that should never be possible. That brings us back to our slides. The question is, what if we need more, or what if we want more access? So zapping kernel memory is fine, I guess. I enjoy it anyway, but it would be great if we could kind of write our own driver modules and load them. That would also mean that we could do like a better SDLC process for our driver development, etc., right? So as we kind of mentioned earlier on in the talk, there are some globals in the kernel which manage what the current driver signing policy is. We can see here on Windows 7 there's a global NT GCI enable, and on Windows 8 Plus there is CI GCI options. Okay, these are kind of tricky to find, both of them. We need to do some memory scanning to find them, but once we do, AquaWrench can just modify those globals in memory and dynamically change whatever the signing policy is. One thing to mention here is that if PatchGuard happens to check those values when they are modified, it will blue screen the machine. However, in practice, those checks are sporadic, and if we revert that policy fast enough, there's really no risk of that happening, essentially. So that's the second demo. We can kind of see a workflow here of how that works, similar to the leak that we described before, right? We load ci.dll here. We get the base address and calculate the offset to some function, ci initialize. And we use anti-query system information here to get the base, the kernel base of CI, right? And then that gives us this kernel address of ci initialize. After that, we have to do some memory byte scanning to find the pointer to another function, cip initialize, right? And repeat the process. We do some more memory scanning until we find this global here, CI GCI options. Okay, and once we find that global, we can just use AquaWrench to change its properties in memory. Okay, so let's have a look at that demo as well. Okay, so we're back on our Windows 10 host here, and quickly I want to show you this CI flag in AquaWrench. It allows us to get some extended kernel mode signing information from the host currently. And we can see that driver signing is currently enabled and enforced, right? If we try to open this OSR loader, and we try to start this evil.sys driver, Windows tells us you can't do that, okay? It doesn't have a valid signature, which makes sense. Now, that's not a big obstacle, of course. If we have another look at AquaWrench, we can see there's a flag here, set kernel CI or SKCI, which allows us to flip this global in memory and turn it on and off at will, right? All our functions support from Windows 7 to Windows 10 and all of the server versions, so that's all taken care of under the hood. So let's give that a try. So we'll set it to false to turn signing off, and we see that that succeeded. And if we come back here and try to start this service, now it succeeds, right? And if we look at CI again, we can see that test signing has now been enabled and driver signing enforcement is now turned off, right? So what we're going to do is quickly stop this service and revert our changes. So we've turned driver signing requirement back on now, essentially. And if we look at CI, we can see, again, it's the way it was before, right? Now, we see this test mode here in the bottom right, but that's just because we changed that global in memory. If we refresh here, you see it disappears because we reverted that value. So you can imagine if you do it fast enough, there will be no observable change on the OS, essentially. Now, we don't really want to rely on the user to, or on the operator rather, to be sensible and do it fast enough, or maybe forget about it and blue screen the machine when PatchGuard finds it. So I implemented a wrapper that does all of this for us. So it's called load unsigned, and it loads an unsigned driver into the kernel, doing all of this patching and reverting at the same time. So here we basically just give it the path to the driver, right? And that's it. So here you can see it's doing the same thing. It's changing the signing requirement. Driver signing is disabled. It then creates a service for this driver and loads it, and then it re-enables driver signing requirement. So the OS is none the wiser. Okay, so we're back on the slides, and I just want to do a final demo to kind of show some other features that we have in AquaWrench. So as attackers, we would generally prefer to generate as little signal as possible. Usually we do that by using tradecraft that we think won't generate signals, or where the target machine is not capable of capturing signals that exist. But in this case, we want to kind of see if we can take a different approach and kind of render any OS components or AV and EDR components inoperable to the point where they are unable to capture signals that could get us caught as attackers, right? And we'll look at two simple examples. The first example is hooking NT-trace event. So NT-trace event is the gatekeeper of all ETW data. When you record ETW data, eventually it passes through that function in the kernel. Okay, so if we hook that, we can just null all of that data that's coming through. The second demo that we want to do is zero out kernel notification routines. So as a driver, you can register to be notified when certain things happen, like process events, image load events, thread creation events, etc. And AquaWrench has the ability to enumerate all of those structures, and we can zero them out again to prevent that kind of logging from happening. Now, these two examples are based on public work from BATSEC and BRSN, so just want to say thanks for their great research. So for demo 3, again, it's kind of complicated. We're looking at a thread creation notification routine here. So we do something similar to what we've seen many times already. We load NTOS kernel here, and then we use LDR load DLL to find the offset to this function, psset create thread notify routine, and anti-query system information to leak the kernel base, right? And then that gives us the address in kernel space of nt psset create thread notify routine. And then we do something similar to the previous example where we do some memory byte scanning, and that gives us this second function here, psp set create thread notify routine. And then again, the same old thing, we do more memory byte scanning to find this global here, nt psp create thread notify routine. Now this global is a pointer which points at a callback array, right? An array of callback structures, this purple block here, right? This purple block is basically the start of an array of those structures, and those structures are these yellow blocks here, right? X callback routine block. Now the details are not too important here, but just to give you an idea of how those leaks work. So let's jump into the last demo and see what that looks like. Okay, so for the final demo, again, we're back in our virtual machine and we've installed sysmon, and we configured sysmon using Swift on Security's sysmon configuration file. And we can see here in the event viewer that there are events coming in, right? If we look at this, like a process creation event here, for instance. Now, if we just quickly clear this log and launch Notepad, for instance, we can see that we have process creation results here, right? SVC host and Notepad. Okay. Now, since we're focusing on process events for this demo, I'm just going to quickly create a filter here for event ID 1, so we only see process creation results. Okay. So we've established that sysmon is logging process creation. Okay. So what we're going to do now is load our NT-trace event sinkhole driver, which is going to use infinity hook to hook that syscall and basically just send all our events to dev null essentially. So let's give that a try. Oh, okay, of course. So we use false to indicate that. So we use false to indicate that we want to actually hook NT-trace event. Okay. Now, if we clear this log again and we launch Notepad, you will see that we actually get 0 events, right? No events are coming in. And then if we turn this back off by specifying true here, you see now it knows that the driver is already loaded, so it doesn't go through this whole process again, right? So we've done that, and now if we launch Notepad, you see we do have new events, and if we refresh, we can see Notepad launches here, right? So that kind of demonstrates that we're able to hook that function in the kernel and do whatever we wish with the data that's coming in to that function. Now, another option that we have is looking at process notification callbacks, right? So let's have a look at that. So here we do this leaking that we saw on the slide, and we see all of these callbacks that are registered in the OS. And if we look here, we see sysmon has one registered as well, presumably to generate those process creation events. Now, what we can do is actually just null this pointer out with another function that we have here, write address, and we can write a D word or Q word to whatever value we specified. So if we do write address and we specify the index in that array, and then we write a Q word of 0, we've now nulled that entry out. If we look again at list process notify, you see that the sysmon driver here doesn't show up anymore. Now, if we clear this again and load Notepad, we can see that we have 0 events, just like before, right? And in this case, we can also restore the value if we wanted to. So in this case, we'll restore that structure pointer. Okay, and again, if we do this, we see that this sysmon notification callback pointer has been restored now, essentially. Okay, and if we clear here and launch Notepad again, we do see that again we have a Notepad event. So this event is coming through again. Okay, let's get back to the slides. This is pretty spooky, right? I think we can kind of agree on that. I just want to give a brief overview here. So we have this infinity hook sinkhole driver, which is currently implemented. I might need to make some modifications to it, but that's currently implemented. What's on the roadmap is reflective driver loading. The work on this is partially finished, essentially. You can see some details here, like some ways you may do that by patching drivers in memory to have them load shellcode, or abusing some NTGDI syscalls, which you can kind of rewrite to execute functions for you. One thing to mention is that these reflective drivers need some special boilerplate code, but that's not really an issue, right? Just more gotcha. And then further to-dos on the roadmap is we have integrating reflective WinDivert payload. So WinDivert is a kind of network driver which would allow us to create some kind of passive backdoor on the machine. And of course, I will need to write bindings for that driver in C#, right? Aside from that, we can plunder capabilities from third-party frameworks, such as Blackbone. Blackbone is a memory hacking toolkit, and they have a driver component as well with lots of interesting features. So Microsoft is well aware of these techniques. The reason for that is that we are borrowing heavily from kernel exploitation primitives. So this is in no way new information that I'm sharing here, just applying the techniques that exist publicly already. And we can see a slide here from Dave Weston that he presented at Blue Hat Shanghai 2019, where he talks exactly about what we've been discussing here, right? If you look at the problem state here, kernel exploits on Windows leverage data corruption to obtain privilege escalation. That's essentially what we've been doing throughout this entire presentation. So mitigations, there are a few like common sense things that you can do to kind of protect yourself from AquaWrench or tools like AquaWrench, right? So something that should work very well is hypervisor protected code integrity, or HVCI. HVCI stops many of these attacks that we've demonstrated, right? The way this works is that there's a hypervisor, in this case Hyper-V, right, which virtualizes the OS. This is transparent to the end user, so the end user doesn't see any difference, basically. But if an attacker manages to compromise the host and get into the kernel, at that point the hypervisor will still protect the integrity of the kernel to an extent, right? So for instance, this attack we've done on downgrading the CI policy to be able to load unsigned drivers wouldn't be possible if HVCI is enabled. The other thing that's really important, I think, and something that's more easy to do, is monitor and control the driver inventory on your estate, right? So if you can implement a list of drivers which you expect to be loaded within your environment, and then prevent the unauthorized load of any other third-party drivers, then that would completely kill this attack, essentially. Furthermore, sysmon event ID 6 will log all driver load events. So if you can't do any of the above, at least sysmon should be able to give you a record of what drivers were loaded by which users. Yeah, okay, a long list of references, right? There's a lot of backstory to what we're doing here, a lot of details which we can't cover in this presentation, but this list should give you a lot of information you can take away and review at your own leisure. So I want to thank you for attending this presentation, and since it's recorded, we can't do a QA, but hopefully I've been present in chat and kind of helping to answer any questions you may have. Thanks for attending this talk.